Welcome back to Cosmos Unlocked. In part 1 of this episode, we're diving deep into the fascinating concept of matter. What exactly is matter, and how does it make up everything we see in the universe? We've mentioned that everything around us, from stars to particles, is made of matter, but there's so much more to explore. From the fascinating theories of Peter Higgs to the remarkable lunar experiments, the question of mass remains one of science's greatest mysteries. Before discussing the Higgs boson, let's first talk about an example of how forces are transmitted. In the previous section, we mentioned that matter is divided into 12 fundamental particles, all belonging to the category of matter. However, in our universe, aside from tangible matter, there are also 4 fundamental forces. To recap, these 4 forces are gravity, electromagnetic force, strong nuclear force, and weak nuclear force. How are these forces transmitted? Scientists have discovered that the transmission of forces also requires particles. For example, imagine an upper quark and a lower quark tossing a basketball to each other. When the upper quark throws the basketball, it slightly pushes the lower quark away. In this process, the 2 particles don't physically touch each other but instead transmit force through the basketball. Of course, this is just a macroscopic analogy. The real world doesn't work exactly like this. So, what are the particles that transmit these forces? It has been found that photons transmit electromagnetic force, gluons transmit strong nuclear force, and bosons, specifically W and Z bosons, transmit weak nuclear force. As for gravity, scientists have yet to find its transmitting particle. However, humanity is particularly good at making charts and tables. Scientists noticed a missing spot in the table for a particle, prompting a relentless search for it. When the Higgs boson was finally discovered, the New York Times called it one of the greatest examples of what scientific progress can offer to modern civilization. Scientists, through theoretical models, predicted the existence of the Higgs boson long before it was discovered. This demonstrates how the process of identifying patterns can guide humanity in understanding the universe. The journey of searching for the Higgs boson was a winding one, and while the details are complex, the idea stems from studying the particles that transmit forces, like photons and bosons. These particles exhibit varying behaviors. Some, like photons, are massless, while others, like bosons, have considerable mass. But why do particles used for transmitting forces differ in mass? Physicist Peter Higgs, along with other scientists, spent years on this question and eventually found a mathematically consistent solution. They introduced a particle, the Higgs boson, and a field, the Higgs field, which is somewhat analogous to an electromagnetic field. The Higgs field interacts with particles, and this interaction determines their mass. Mass is treated as a tag for particles, with some particles having a stronger interaction with the Higgs field, making them harder to accelerate and thus more massive. Others interact weakly with the field, making them nearly massless. This theory is quite intriguing. When asked why particles have different masses, the Higgs theory attributes it to varying interactions with the Higgs field. However, if one asks why these interactions differ, the answer boils down to an inherent property of the particles themselves. Essentially, the theory shifts one question into another without providing a fundamental explanation. It doesn't establish a specific rule governing particle masses. Mass is treated as a parameter, arbitrarily assigned. Even if the masses of particles were different, the theoretical framework of the Higgs field would remain intact. Of course, if the mass of certain particles changed, our universe might look very different. But according to the Higgs theory itself, particle mass is simply an adjustable parameter. In the previous section, we discussed the particle chart. When particles exhibit certain patterns, they may be composed of more fundamental particles. Perhaps future scientists will discover these more basic particles and rules, which determine why quarks have different masses. For now, though, such rules remain elusive. Imagine someone wondering why one drink tastes like apple while another tastes like peach. An expert in beverage formulas might explain that it's due to different flavoring agents. Perhaps something similar will happen with particle masses. Now that we've discussed inertial mass, let's move on to gravitational mass. There are two ways to measure mass. The first is by testing inertia, pushing an object to see how easily it accelerates. The second, simpler method is to measure weight using a scale, which essentially measures the strength of Earth's gravitational pull on the object. The greater the mass, the stronger Earth's gravitational attraction. Looking at particles again, you can think of gravity as being analogous to electric charge. When two particles have a charge, they attract each other. The greater the charge, the stronger the attraction. Similarly, when two particles have mass, the gravitational force between them is proportional to their mass. But are gravitational mass and inertial mass truly the same? Fundamentally, they are not. Theoretically, inertial mass refers to the effect of the Higgs field on a particle, essentially, how strongly the particle interacts with the glue of the Higgs field. A particle that is more stuck by this glue is harder to accelerate, and its inertial mass is higher. Conversely, a particle that is smoother and interacts less with the field has a lower inertial mass. Gravitational mass, however, involves the concept of a gravitational field. Within this field, the mass of a particle determines the strength of the gravitational pull it experiences from other objects. For instance, on Earth's surface, you can imagine the Earth creating a massive gravitational field. The stronger a particle's gravitational pull from the Earth, the greater its gravitational mass. Here's where the wonders of science come into play. When we measure mass in both ways, inertial mass and gravitational mass match perfectly, down to the tiniest precision, even though they arise from entirely different theories and assumptions. This coincidence is puzzling because, while both are called mass, they are fundamentally different parameters. Inertial mass measures an object's resistance to motion, while gravitational mass measures its tendency to be moved by gravity. This equivalence can be tested with experiments, such as the famous lunar drop test. On the Moon, where there is no air resistance, a small plastic ball and a heavy iron ball will fall at the same rate and land simultaneously. This happens because, although the iron ball has a larger gravitational mass and experiences a stronger gravitational pull, it also has a larger inertial mass, which resists acceleration more. Conversely, the plastic ball has a smaller gravitational mass, experiencing less pull, but its smaller inertial mass makes it easier to accelerate. These effects precisely balance each other, resulting in both objects hitting the ground at the same time. This naturally raises the question, why is inertial mass exactly equal to gravitational mass? Unfortunately, our current understanding of physics cannot explain this phenomenon. We can only assume that the two masses are identical. Einstein himself made this assumption when developing his theories. Just as he assumed the constancy of the speed of light to derive special relativity, he also hypothesized the equivalence of inertial and gravitational mass, leading to general relativity. If asked why he made such assumptions, Einstein might have simply replied, "Because I believe it to be true." Theoretically, these two masses could be different without violating physical laws, yet in reality, they are always the same. This remarkable consistency is part of the larger mystery of the universe, which is filled with such coincidences. To summarize, mass has several strange and fascinating aspects in science. 1. An object's mass is not merely the sum of its parts but also includes the energy binding those parts together, though we don't yet know why. 2. Mass, as described in the Higgs theory, acts like a label. Objects with a larger mass label interact more strongly with the Higgs field and are harder to move, while those with a smaller label interact weakly and are easier to move, but we don't know why. 3. When we measure gravitational mass and inertial mass, the results are always identical. And yes, we still don't know why. This is the beauty of science. It's what keeps scientists exploring. The deeper you delve, the more questions you uncover. And in the process of seeking answers to these questions, you often stumble upon new discoveries. Perhaps one day, when we finally unravel the mysteries of mass, we might unexpectedly uncover even greater theories. That's it for this section on mass. Along the way, we mentioned gravitational forces and matter in the universe. In our next episode, we'll dive into the mystery of space. What if everything you thought you knew about space was wrong? This is Cosmos Unlocked. See you then.